in case of a repeated root of phi nm equal to 0, we know that in case of repeated root phi nm equal to 0 as well as phi n prime m is also equal to 0, and we have phi n minus 1m equal to 0. So, for that matter, how we would like to find the value of C for the pair of asymptote having same m but different C. Just see that from Taylor's expansion of this term we have phi nm plus C by x phi n prime m plus C square by x square into 2, obviously factorial 2 gives this, plus we have 1 by x phi n minus 1m plus C by x square, C by x here as h and 1 by x here makes it C by x square phi n minus 1 prime m plus the term C square by 2x square becomes C square by factorial 2 actually x cube, isn't it so? Phi n minus double prime m, and similarly from here we have 1 by x square phi n minus 2m plus 1 by x square into C by x makes it C by x cube phi n minus 2 prime m, isn't it so? Now, since in case of multiple root of m of the equation phi nm 0, we have this equal to 0 as well as this equal to 0 as well as this equal to 0, and then we multiply with x square throughout, and what do we have? We have this term, we have this term, and we have this term, and if we write them separately we find that, see, we have multiplied with x square, so this term is half C square phi n double prime m. We are taking limit, let me wipe out all these terms because they are 0, and we are taking the limit as x tends to infinity. We have multiplied with x square throughout and then taking the limit. This is also not here, this is 0, and we have this term, and there is a x, and we have this term, and there is also x. So we have C half plus C phi n minus 1 prime m, and we have then this term, and all these terms are 0 because x tends to infinity. So from this relation we have half C square phi n double prime m plus C phi n minus 1 prime m plus phi n minus 2 m equal to 0, and this is a quadratic in C which gives the two values of C corresponding to a single value of m, and we have parallel asymptotes with two C1, C2 are the roots of this equation. So that is basically the technique of finding the oblique asymptote. Let us remember that if we have a polynomial of nth degree like this, remember that we have written the polynomial of nth degree like this, that we have the first term a0 x to the power n, a1 x to the power n minus 1 y plus a2 x to the power n minus 2 y square dot 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 a n y to the power n, comprising all the terms which have nth degree, and similarly then we have all the terms with power n minus 1th degree, isn't it so? And then we have this is n minus 1, and then we have the linear term c0x plus c1y, and then we may or may not have a constant term. Now this polynomial of nth degree may be written as, say, y minus mx plus f n minus 1 by q n minus 1. How? It is quite easy, because if this is the term comprising all nth terms, so if you can take a factor like this, it becomes a term of n minus 1th degree, isn't it so? This is the term of nth degree, x to the power n, then x to the power n minus 1 into y. So nth degree, n minus 2 into y square. So nth degree and then y to the power n, and we take a factor y minus m1 mx literally. So what is left is a term of degree n minus 1th degree, isn't it so? And this is also already a term of degree n minus 1th. So we replace this with this, and then this with f n minus 1. What is the next term? The next term is, say, c0 x to the power n minus 2 plus c1 x to the power n minus 3 into y plus c2 x to the power n minus 4y square dot 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 c n minus 2y to the power n minus 2. That is the way, na? See, the first term comprises all the terms with nth degree, the second term will comprise all the terms with n minus 1th degree, and the third term will comprise all the terms n minus 2th degree. And what will be the next term? N minus 4th degree, and thus the last term becomes, say, d0x plus d1y, the linear term, and the constant term is of degree 0. So that is the way of writing it. So if we write this way, not this way, but this way, in a short format, this was the term nth degree. We assume that there is a factor y minus mx, linear factor. Then the remaining terms are all of n minus 1th degree. The next term is n minus 1th. The next term is n minus 2th, and so on. So we have this type of expression, isn't it? The next term will be of n minus 2th and dot dot dot. This is the first linear term, and then we have the constant term. Let us write it as d. So if we divide by q n minus 1 and then take the limit, we take the limit x tends to infinity of this plus there is gn minus 2 by qn minus 1, isn't it so? Plus dot 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 h1 by qn minus 1 plus d by qn minus 1 is equal to 0, and we are taking the limit of all these terms. So you can easily apprehend that since here n minus 2th degree term by n minus 1th degree term gives us that there is an extra x here, isn't it so? And in all these terms we have an extra x in the denominator, and which makes all these terms going to 0 in the limiting case. So we are left out with this and this. See, this may be 0, may not be 0. If this is 0, then we have y equal to mx as a asymptote, and if this has a finite limit, we have y minus mx equal to that finite value as the asymptote, isn't it so? So this is another technique which we will employ in case of finding asymptotes. And remember that while making this while evaluating this limit, we will not only use x tends to infinity, but also the limit that y by x tends to m. Remember, to find the limit of the ratio. I hope you understand, because as x tends to infinity, y by x tends to m, isn't it so? That is the basic definition of asymptote. Another technique of finding asymptote that is a very straightforward and easy technique. If a polynomial curve of nth degree may be written as fn plus fn minus 2 equal to 0. That means we have nth degree term and then we have n minus 2th degree term and no other terms involved here. Then we can straight away write that fn equal to 0, all the factors gives the asymptotes straight away. Gives the asymptotes straight away. All these are obviously about the oblique asymptote, you should remember. We can easily give an example here. Just take this case. Here we have a cubic polynomial, 3 factors, and so this will be a linear term. So this is fn and this is fn minus 2. And in this case, we have 3 asymptotes, y equal to x, y equal to minus x, and y equal to 2x. Clear? So this is a very useful technique of finding asymptotes.